There you go. We still have some seats in the middle. We still have some spots in the middle there up front if you want to sit down. Space. Few more minutes till we start. We got a seat right in the middle or one on the edge there.
Over there, I think.
Yeah, oh, then we got one right in the crowd.
I'll go to the edge. I think.
Hello, everyone. Thank you for coming tonight. Welcome to our first workshop. Machine Learning 101, the what, how, and why of modern machine learning development. First, let me pause for you. So just give a kind of overview of the agenda tonight. For the first 50 minutes, we're just gonna go do a presentation on an introduction to AI and machine learning. Then we're going to take a 10-minute break so we can all refresh ourselves. And then finally, for the last 50 minutes, I'm going to be doing a live coding workshop. So first, what is artificial intelligence? Does anyone want to try and give an answer? You,
Yeah, robots that are smarter than humans.
sure. Why do you say robots?
Well, I mean, it doesn't have to be a robot, it's just. Electrons, there we go, electrons that are smarter than humans.
Right, you,
I wrote like man-made intelligence.
that's a good one. Yep,
That is going to basically receive data,
Mhm.
learn from that data, and then as users ask it for information, it will drive the data and learn it, drive to give an answer based on the patterns of learning that.
that's an interesting answer. Yeah,
Sophisticated categorization.
you got
Sophisticated categorization.
interesting.
So basically, if you want to represent.
Mhm.
I should think of things as you have
Mhm.
semantic tokens of. Things that you would use when you're thinking about it, when you're explaining them, you do have semantic tokens as nodes in a neural network.
Mhm.
And you reassign the weights.
Yeah.
The model can get better at,
Mhm.
broadly speaking, image recognition. Doesn't have to be visual necessarily, but it could be
Yeah.
sort of.
Interesting. Y'all have some very great and very interesting answers, but artificial intelligence is much broader of a thing. So from Wikipedia, artificial intelligence is just the intelligence of machines as software, as opposed to the intelligence of humans or other animals. So that can include engineered algorithms. Anyone who's taken computer science CS1 or CS2 yet? Have to write any algorithm? Congratulations, that's technically AI. Then you have rule-based systems. This is basically just a set of rules. This is a lot like algorithms, but like instead of just having something specially tuned, you just have like a set of rules, like for like categorization. It's just if it's red, do this, if it's blue, do that. And then finally, then you have machine learning, which is where you have your data and then you have the machine learn from it. So the old-fashioned way of things, ever so long ago, asterisk, including today, we never got out of this, is called symbolic representation. And what symbolic representation is basically where we have a set of rules, some human understanding of the problem that we tell the machine, this is how we want you to see the problem. And then we give it some input. And then we look at the output of that and make decisions on how good the rules we made were for that. And this is the way they did it up until like the 90s. And it's a good system. Humans are smart. We can design some great systems, but it's not always great, especially if we're trying to get to things that are hard to learn, like trying to program a computer to recognize the difference between a picture of a cat and a picture of a dog. Can anyone write a program from that doesn't involve machine learning? Yeah, exactly. Yeah, like if I have a picture of a cat or a dog and I give it to the computer, I'm telling you, can you write a program that doesn't involve machine learning that can identify the difference between a cat or a dog? How? How are you gonna encode patterns?
What?
If you're gonna do patterns, you have to define what the pattern is.
Well,
Yeah, but it's hard. Yeah, yeah. So this is where machine learning comes in, where unlike before, where things were rules driven, now things are data driven. Where basically, unlike before, where we give the rules in our inputs to get the output, now we just give it the inputs and the output, and we tell the algorithm to figure out the rules. And this was a complete transformation, because this has basically allowed us to not have to take the process of figuring out what the rules are and like how to design the program. We just told it, figure it out yourself. And so there's many types of machine learning out there. The most common one is supervised learning, which is basically where you have your inputs and you have the outputs that you want it to do, and you teach it, okay, figure out a way to match these inputs and these outputs together, like find some system that matches them. And then when we try and feed in something new into it, like a new picture, we ask it, okay, figure it out, give an answer, give an output based on this input, based on what we learned here. Like, for example, we have pictures of apples and we have labels that these are apples. And we tell the machine, okay, based on the fact that these are pictures of apples and we know are apples, and we would also have pictures of not apples, and we would say they're not apples, figure out some way to learn, figure out some rules that differentiate between what is an apple and what's not. And so when we give a new apple, it would be able to do that. And this is probably the most popular system because it's very easy to understand. Most things we have something we want to get in and want to get out. But there's also other systems, for example, unsupervised learning. Unsupervised learning, unlike supervised learning, is where we don't have an output we know of. Like, we don't know these are apples, we don't know these are bananas, we don't know these are peaches. What we have the model do instead is learn to sort of categorize the data into what we know are similar. Like, for example, here, we can tell that these apples all look similar, and so do these peaches and bananas. And so the machine learning model learns how to sort of categorize all these things together. And so that's called unsupervised because unlike supervised, where we have an output that we're going to teach the model to say, this is correct or this is incorrect, we have no way of telling it it's right or wrong. The model just does it on its own. And then finally, the other popular one is reinforcement learning. And this is, in a simplified sense, robots. Robots are basically, it interacts with the environment directly and it learns, and then it adjusts itself, and then it interacts again, and it learns, and it basically does that in real time, and it reinforces good behaviors. Like, if you're teaching a robot to grab a water bottle and place it somewhere else, if it missed the water bottle, you'd say it did badly. But if it did it, you would say it did goodly. And so it's like training a dog. You're going to reinforce the good behaviors and punish the bad. So tonight, we're going to be going over supervised learning specifically because it is the most popular. And I will be going over the supervised machine learning feedback loop, which is basically just the pipeline of a machine learning developer as they start from just having nothing to finishing their AI model and then starting all over again to iterate and improve. So first is data ingest, which is basically gathering the data you want to work with. Because if you're going to do a machine learning project, you need data, right? You can't make a model when you don't have any data to make it from, right? And so you can get data from anywhere. There's pre-made data out there that you can just find online. OpenAI, for example, basically just scraped everything from the internet, whether it was copyright legal or not, and then just train the model off of that. You also have public data sets, like a lot of medical companies and medical hospitals they'll release some of their data out to the world, and you can train models off of that. Then you also have government data, and then you can also just collect your own data. That's very popular, especially if you have a niche project. For example, I'm working at a solar power lab where we have a couple solar power plants, and we gather data from those so we can do our own models. And so once you have all of this data, you then get to data cleaning. Yeah.
You're saying data, how much data are we referring to?
That depends completely on the problem. Sometimes it can be very, very little, maybe tens or hundreds. Sometimes it can be like ChatGPT, where you need billions upon trillions upon quadrillions of words. So it completely depends on the sort of problem you have.
And then when you're trying to refine your model to get more accurate, would the increase in data usually make it become more accurate, or does that come from data cleaning?
So data ingest and data cleaning first are very conjoined together. You don't do data ingest without doing data cleaning unless you don't need to do data cleaning, which is very, very rare. But it's a discussion. Most of the time, yes, having more data will make your model better. Because the more data you have, the better your model can learn the rules that it needs to learn. But it can also depend. Some models don't get better with more data, just because the more data you have, the more noise you can get into it. Because sometimes the data is just very noisy. Like it can go one way or the other a lot of the time, or you could have collected your data wrong. And so now, despite the fact that you have more data, it's not good. So this is where we get to data cleaning. And so data cleaning is basically a standardization process. Now that we have our data, we need to put it into some fashion that's very standardized and very like uniform. There's no issue. Because the biggest problem in machine learning, more than anything else, is noisy data. You are going to be spending 80 to 90% of your time ever fixing anything. Because you're going to be missing data. Your data can be differently labeled. You're going to have things at different ratios or have included extra text. You're going to be spending quite a bit of time just cleaning this up. Luckily, not tonight. Luckily, tonight, all the data I have for you is nice and already clean. But if you're ever working in the real world, you're going to have to deal with all of this. So once you've spent the first 80% of this entire pipeline cleaning the data, then you get to do what is called data splitting. So we have our full data set. How should this data be divided? Because we need some way to like test that our data is working, right? So how would you say we should split the data then? Yep.
If you find the trend first to the data set, that some data are more similar to others of data, I would put them in one section and the others in another section based on their similarities.
Maybe, but if you sort your data like that and then split it that way, if you're going to have the model learn on one thing, on that one sort of pattern, can it learn off of the other? Maybe, but if you like sortify apples and bananas, it's only gonna, and you teach it on apples, and it's never gonna have an understanding of bananas, because it's only ever seen apples in its entire existence. Anyone else? No,
You assign labels.
that's part of the data collection process. So normally, what we do is we split the data into what are called 3 sets. First, we have our training set. This is what the model sees when we're teaching it the rules. This is what is commonly called training or fitting. This is the set where we say, okay, model, this is the only thing you're ever going to see when you're learning, learn the rules. And then we have the validation set. The validation set is basically the set that the model hasn't seen when it's learning. And so it's unlearned new data that we're going to use to help refine some of the tunable parameters. Because machine learning models don't just come in a preset package with no tuning knobs or anything. There's like, for example, for the person talking about neural networks, you can have the number of layers or the number of neurons, or you can adjust regularization. I'm throwing all these terms out, but all you need to know is that machine learning models generally have a lot of knobs you can tune that can affect how well it learns. And the way you tune those knobs is with your validation set. Because the validation set is basically the way it's not seen by the model in training, but when we test on it, it will be new and we can see, okay, the model's getting better or worse on new data. And then finally, once we go through all of that, we go onto the test set. This is also known as the holdout. Basically, this is supposed to be the very last thing you touch. Once you've done your training and you've done your validation, you have the best model you know of, then you go on the test set. And once you run it on the test set, theoretically, you're supposed to be done. Once you run on test set, you can't do any more because that test set is the final benchmark. Because if you start doing the iteration back on your test set, well, then that's called leakage. And because now you're learning off of your test data when you're not supposed to be. It's supposed to be the final benchmark. Now, I will make a comment that this is never upheld greatly in practice because you need benchmarks of some kind. That's basically how we know how to compare models is with test sets. And so we do have some amount of learning, But the amount of leakage there is much more minimized compared to if we were learning off of like the validation data. Yes.
How do you split your data to avoid overfitting and overfitting?
That is a great question, and I love that you know how to turn that. So so there's a lot of ways to train to split your data to deal with underfitting and overfitting. And I'll be getting to those later, but basically underfitting is your system didn't learn the rules well. Like it basically learned a sort of overview, but it's not correct even to its training data. And overfitting is that it learned the rules super well for what it had seen, but then it basically fails on anything outside. Like it could learn, like if you have like a quadratic curve and you have some points on that, some like points around the curve, an overfit model would learn to hit every single point, but like in a zigzag pattern, but then it didn't actually learn the curve itself. So for dealing with underfitting and overfitting and the splitting, a great question. How would I answer this? There's sort of two ways. Well, the main way is that the concern there is unbalanced data, where it's like, for example, let's say you had a data set of pictures of apples and oranges, but like 80% of the pictures were apples and 20% were oranges. If you just randomly split the data, it's very likely that, I'm sorry, I see 4 messages. Okay, sorry. Apologies, I had to make sure everyone could hear us. So like if you just did a random split on like on that 80-20 ratio, then it's very possible your training set could be just all apples. And then so your test set has all the other bananas and maybe some other apples, but now your model is not going to be able to learn anything about bananas because it's only ever seen apples. And that was just because you did a random split. So what we do is called a stratified split, which is basically, instead of just splitting randomly, we take like every like subset in our data, like the set of bananas and then the set of apples and then whatever else. And we then do our ratio split off of that and just give one to one side and then to the other. For example, with that 80-20 ratio of apples and oranges, we take the oranges, split them off into our test and train. And we also take our apples, split them off and test and train. And so that way we have both apples and oranges, both in our training and our testing set. And they'll also be at the same ratios relative to one and the other, close to both sets. Does that answer your question? Cool. So once we do that, then we get to model training, which is where we go through and experiment with many different types of machine learning algorithms and have them learn from the data. And so there's many different types of machine learning algorithms. On sort of the simplest case, we have these sort of baseline algorithms like logistic regression, decision trees, support vector machines, KNNs. These are all sort of like very baseline. I'll cover these in a future workshop. All you have to know is like these are basically very immediate and learn very quick, but these are also relatively simple and won't learn the rules very well on very complex data. So what we do is then we kind of get to the next level of complexity, like random forest, boosting models, and ensembling. These sorts of models are basically combinations of models that are built off of like these baselines. For example, random forests are just sort of combinations of entire arrangements of decision trees. Then ensembling is just a sort of arrangement on all of these sorts of models. And then finally, if none of these are working very well, you can try neural network / deep learning. And this is what many of you would already be familiar with. Like this is the things that you hear about today everywhere. Like this is what modern machine learning, this is what I would say is most done nowadays, because that's where the hardest data is. Like training a language model, you'll need a neural network for that. Training an image classifier. You could do that with traditional, but anything complex nowadays is going to have to be done on a neural network. And I will be covering these in a few weeks, but these are the most complex to learn. And so after our model training, is we get to our model testing, where we take some of our data that we've had hidden and we evaluate the performance. That's the test that I was talking about. And so for that, the main challenge of training that we check with testing is fitting. And there are basically three scenarios that can occur. One is overfitting, where our model learned very well on the training set, but didn't learn well at all, didn't learn the rules actually well, and will do badly on the test set. For example, as you can see here, if we see the sort of curve that was formed based on those black dots, which were our training, as you can see, it's very good and hits all the points perfectly. But then if we look at our star, which is our test set, that's a very large gap. And that's because the model learned very well the rules to fit the training data, but then it learned them too well and now doesn't actually do well on testing. The other issue is underfitting, where the sort of rules that it learned are basically too simple and therefore don't actually match the data. Like here, you can see this is a curve, but the whatever model we used, the rule it learned was basically just a straight line. So not only does it not capture the training data, it doesn't capture the testing data as well. And this is just not usable at all. And then finally, we have it when, it's just right, where our model is able to learn the training data pretty well. It's gonna still have some error, but now it has the best sort of curve on it. And then it also helps to minimize the testing error. So our model is very usable in an outside scenario outside of our training data. Then finally, once we've tested our model, we've gone through and seen like, good, it's working well. This is where we get to deployment, where we try and deploy it to a production setting. And so this is what most of you and what all companies really are interested in. Like, great, you made a model, but how do I make it public? And you can do that in many ways. You can release the weights and have someone load it up themselves. You can have it load up onto a website and people feed it in. You can have someone sort of interact with it, or you can have like someone interact with it, have them give feedback, and then have the model do the whole loop again based on their feedback. But there are basically 1,000 ways. You can host it locally, you can host it on the cloud. This is where you actually get it out. And so once you release your model, this is where we start the loop again. But once you have your model, you can have people test on their own data, and then you can get feedback from them on if it was correct or not. And now that people are feeding in their own data and having their own comments on it, then that's new data you can train a model on. You can ingest that in, clean that, train a new model, test it, and then deploy an even better model based off of whatever new user's data was. And that cycle goes on and on and on as you improve your models. Like that's what ChatGPT does. ChatGPT at the beginning didn't work very well. I mean, it worked, but it wasn't that good. But they had a lot of feedback from users. And so they were able to get more and more data and refine their model until it was as good as today. So, yeah.
Will these slides be posted?
Absolutely. All slides will be public. Our Jupyter Notebook, the code we'll be working on will be public, and I'm having a recording done right now. Yep. So tonight's algorithm we will be covering is the simplest one we have, linear regression. So quick question for those of you who are statistically minded, who remembers what linear regression is? Hey, some of you do. Yeah, so linear regression is basically boiled down to basically algebra mx plus b. It's just your slope-intercept form of a line. Who remembers that? I'm hoping most of you. Great. Getting a little concerned for the Florida education system otherwise. So basically, with this, there are sort of two parameters our model can learn, which is that allow us to tune our model to our data. We have m, which is the slope of the line, and b, which is the y-intercept. And so we're going to work to adjust these until we get to the minimal error value. Okay, we're going to tune them and tune them and tune them until they look just right. And the way we normally do that is with something called gradient descent. And so what gradient descent is basically we start at some random point, like right here at the top. And this function here, this j, is what we call our error or our cost function. This helps to measure like how wrong the algorithm is. And so what we do is that we take this point And we basically look at it and say, okay, how wrong are we and which way should we go? And so what we do, we take a small step based on the improvement of based on what we know is wrong, and we take a small step to do better. So we keep doing that over and over and over again until we try, and in the process, we're minimizing our error, which means we're improving on our model. Until finally, we get to a local minima, which is basically you can't get any better than this spot right here. But there may be better spots, like for example, this spot is good, but this spot is better. But based on how our random starting position and how we went down gradient descent, we just got to another minimum. And so a big challenge in machine learning, especially neural network, is training a model that will actually reach to the actual best minima and not some local one. But I'll talk about that another time. But to give an example of what gradient descent looks like, I have this wonderful gift here. And as you can see, it's very wrong, and then it adjusts more and more and more and more until it fits very well to the line as best as it can. So for linear regression, there's sort of two common ways we measure this error to help it learn. One is called the mean absolute error. And this is as simple as it sounds. This is just the average error of what we think it was, what the prediction was versus the actual value of it. And so we just get the absolute difference of that and average it. This is very easily understood. Like, it's pretty obvious, isn't it? Like, this is the way you would do it. The problem with this, with doing mean absolute error, is that it doesn't punish very big errors well. It doesn't punish them differently. For example, an error of 4 and an error of 5 are pretty similar, but we may want them to be very different. Like 4 might, like the worse it is, we want to really tell the model, stop doing worse. So this is where we get to the mean squared error. And so the mean squared error is very similar to the mean absolute error, but instead of just taking the absolute difference, we take the square of it. And so this helps us to punish the model, basically saying if it made a big error, no, it didn't make a big error, it made a really big error. And so this forces the model much more quickly to stop making mistakes and get it to a very good point where we can say, okay, now you're going to learn very quickly. And so this is a very, yeah.
I'm sorry, I'm just kind of confused with the two different errors. Is one of them just like able to tell much more precise that it's making errors?
I wouldn't say it's much more precise in making errors, but both are used. It's just one is able to tell the model much more quickly if it's making a big mistake.
Oh, I get it. By one error.
Yeah.
Okay.
Yeah. This one is just much more punishing on making a mistake. Like, for example, if you got a 50 on exam, under mean in absolute error, that would be a 50. But then from like mean squared error, for example, that would be 0. There's much harsher fail rate. So that's the normal way. To make a special note, no.
Why would in what scenario would the regular one be used instead of this more harsh one?
So one of the reasons why it might be used is that this is punishing the model too much. So sometimes, depending on the model, it might start out just making big mistakes. And so when you do squared error, you're telling it it's doing super, super badly. But because the model learns based on how much it's making a mistake, if it's thinking it's making too much a mistake, it's going to try and move too quickly to a correct answer and then jump over a correct answer, jump over a better spot to another bad spot. So sometimes we want it to think it's doing better than it is and have the error just decrease, have the error be smaller. It's all about how you design it. Yeah. Anyone else? Yo.
Are there any situations in which you can use types of errors for maybe like different phases of learning?
Yes, sometimes you do use different learning algorithms, but I would say most of the time what you'll often actually see instead is both be used in different portions of a model. And this is more frequent in neural networks because neural network will have like different structures internally. Like they'll have like different branches of how the structure work, and those will learn separately. And then you can combine different error functions together for that. But for the model we're covering right now, no, normally you just have one. So to make a special note of least squares, make linear regression. Linear regression is also something that can just be solved directly without gradient descent, called the least squares method. And basically, this is just minimizing the square of the residuals. And residuals are basically just the difference between our prediction and the expected value and the square of that. And then this will solve the best solution directly. And so while linear regression may be solved by least squares, we have other sorts of regressions that do require gradient descent because they don't have this sort of just immediate solution. For example, logistic regression. So before we get to that, I want to ask everyone this. Based off of linear regression, this sort of just straight line, how could we classify data with it? Yo,
Can you further explain what you mean by classify?
apples and oranges. If I gave you a picture, is it an apple or is it an orange? Yo,
Color? Yeah, when you classify it by the different features that you have in your data.
yeah, but like with just a straight line, could you do it? If I gave you some data and I just gave you a straight line, just like the mx plus b, and I gave you some dots in 2D, and I gave you a straight line on it, could I have you then make a decision based on that straight line, whether something is something or isn't something? Yes, that's a good one, but in some sense, then that's actually 3 points of data. Because you have your one, because then you have your 2 points, and then you're classifying your dots on an extra axis. So the way we classify data is that we transform linear regression into logistic regression using this special function, the sigmoid curve. And basically, the sigmoid curve is this S-shaped curve that you can see here that goes from 0 to 1, and it does it very smoothly. And so what logistic regression does is that it basically returns your output into just a binary value of 0 or 1. It's like true or false, yes or no, alive or dead. And this is the magic equation. And so we're basically going to take the line, your binary response, and make it into one using sigmoid. And this is basically just like a logarithm on it. A logarithmic transform on the odds of the answer being one or the other, like yes or no. And so this is how we train it. Now we have basically the log. We take x and then we put in the log of the odds of the answer being one way or the other based on x. And the big secret of logistic regression, it's just linear regression, just logistically decised. It basically is the same idea of we have a line, but now we have our dots. It's either one way or another. We just wrap up this line into this curve. It's simple as that. Instead of having the line to go up and up and up, we basically say, okay, you're going to be now in an S-shaped curve. And since now we're above this value, we're going to kind of just flatten out. And since we're super close to 0 here, we're going to flatten out. It's actually very simple. And so for this, we're going to look at an example of spin scooter crashes. Let's let L be the odd that you're going to crash on an electric spin scooter. How many of you have crashed on those scooters before? Do they have a scooter still? Okay, I'm making sure I never used one because I didn't want to pay money for them. So then let's just have two variables here. X1, which is just like the average speed of the scooter driver. They're either going fast or they're going slow. And let's X2 be if they're driving for the first time. So like it's 1 if it's yes, this is the first time, and then 0 if it's not. And so we're basically then going to have three variables here, very similar to your mx plus b, of just a bias of to shift the odds, and then b1 of sort of the multiplier if how fast they're going, and then another multiplier of like if they're a new driver or not. And we have the model learn basically on the odds of if the person is this versus not, and to match these what are called parameters here, to match these two values as close as possible. And so this is how we learn. We're basically teaching it, instead of just do a line, learn the odds of the odds of the line, and then this helps us to make a classifier of saying, no, it's not going to be that way, or yes, it will be. So finally, to address something before you guys get very excited by everything, there are some problems with it. First of all, correlation does not mean causation. Just because there is a trend in your data, doesn't mean it'll make a good model. To give you all an example, let's look at this website. So let's see. Bachelor's degrees awarded in psychology, the number of groundskeepers in Utah. Those are super related, right? You know absolutely that because there's more psychology degrees, and we're just losing all the number of groundskeepers in Utah, right? Right? Yes? No? That sounds silly? That sounds like nonsense? Yeah. That's because these two features aren't actually connected in any way. They're not, one doesn't cause the other. They just happen to look similar. So that's a big thing you have to be cautious about when you're doing, am I still sharing? Yeah. When you're doing machine learning, is that you have to make sure that you don't make the incorrect assumption about whatever your data says. And then there's also some limitations on linear models themselves. One, they don't perform well on non-continuous predictors. Basically, you saw that they're straight lines, but if I gave you like a parabola, you're not going to be able to draw a straight line for a parabola. You're just not going to be able to capture that. And most data is not continuous. Most data is weird and complex, and just basically, you're never going to be very lucky to have a linear scenario. The other thing is that even some of them can be just very bad at predicting for like binary. Like especially for like linear regression itself, it's not great at doing basically if it's 0 or 1. Like if I just have values that are like 0 and then just have values that are 1, you can't draw a line for that. Not well. And then finally, just like the data itself could have non-linearity. Like maybe your output is non-linear, like maybe your output is a parabola, but what if one of your input data is a parabola? Like if your input data itself is a curve, you can't have the model really learn a linear relationship from the input to the output. So one of the potential solutions that maybe we transform it out of the way, maybe we multiply it on itself, or maybe we shift it around somehow. Or we just use a different type of regression model. We don't use linear, maybe we use a quadratic or like a bigger polynomial. Like you've seen like what? AX squared plus BX plus C, right? That's also another algebra thing. And so there's other types of algorithm that can fit it better, but we'll talk about those in the future. So anyone have any questions? No? We're all good? Cool. Then let's check out the notebook. Gonna take a 10-minute break so far. And then we'll get started on the coding session. Yeah. You can also access the you're gonna want to be on your laptops for this. So you want to go to the URL tinyurl.com/ML101. O as in the OH. Okay. Zoom recording. All right, cool. Great. Thank you for everyone who stayed. Welcome to the Machine Learning 101 Jupyter Notebook. This is basically what a Jupyter Notebook is basically a file that lets you interactively write Python and lets you like write a little bit of code, then run that little bit of code, maybe change something about it, run it again, run some more code, maybe go back and change things. It basically just lets you run little bits of code each time, all on their own, and allows you like run and edit your code on the fly. So, and this is very popular in machine learning development if you're like just testing something, because you don't want to have to write an entire file, realize something's wrong, and then have to go search for it. You just want to write the little bit. So before we can do any machine learning, we basically have to import a few packages because Python isn't natively, doesn't have any like native support for machine learning. This is all done through packages. And so,
So for machine learning, is Python just like the industry standard?
yeah, Python is the language you do it in. Not because of the language itself is any spectacular, although it's very easy to write. It's that Python is very, very convenient for package installation. Like all these packages I have here, I can just import them. Although normally if you're running it on your own machine, you also have to install them. but installing them is very easy. But for all our purposes, we're just gonna be doing it on Google Colab, which just has everything installed already. So to go through it, there's like 5 libraries I want you to know about right now. One is NumPy, and NumPy is basically just it's just a library that allows us to do operations on arrays, which if anyone's not familiar with what those are, they're just lists. Technically, they're different. Lists and arrays are different in technical senses, but for all your purposes, they're the same. Except Python lists can change their size, arrays can't. Arrays are a set size list and you can't change it. And NumPy just lets you like change values on them, edit them, move them around, and just do a lot of things on it much faster than you can in native Python. Matplotlib is basically just a plotting library, like drawing like a scatter plot or a bar chart. That's what Matplotlib is for. Very easy to use. Then you have Seaborn. Seaborn is like Matplotlib. It's actually built on top of it, and it lets you also just like make graphs and plots, but they're nicer looking plots, and they let you make some more advanced plots that Matplotlib doesn't natively support. Then you have Pandas. Pandas is basically just a library that's a spreadsheet. Like you've all worked with Excel, you know, rows and columns. That's what Pandas is. It's just a code version of that, and it just lets us like organize our data, look at it, look some properties easier than just like NumPy or another. And then finally, we have sklearn, also known as scikit-learn. This is the machine learning one. This is where we can do all of our machine learning problems. And except neural networks, they do support neural networks, but you don't use scikit-learn for neural networks. There's other libraries that I'll talk about in the future that use those. So first, we're just going to simply run the cell. And so we're going to let it run. And then this is going to just import all the libraries and everything we need from them. As you can see here I'm just importing just the libraries themselves. And then from sklearn, because it's so big, I'm importing what I need specifically, which is our data sets, some display information that will be useful for later, our linear regression, our logistic regression models, our code for splitting it, and then some extra information for displaying metrics. So first, we're going to talk about what we talked about at the first model, regression. So regression is basically just, we're going to do a linear value. We're just going to try and do continuous, like we have our dots, and we want to try and figure out some curve that will describe all those dots together in sort of like a continuous fashion, in a just basically a flowed fashion. And so this is very common in things like forecasting stock prices, because stock prices are a curve. Trying to estimate a housing price, or maybe trying to calculate a credit score. There's no like set categories. I guess for credit score there is, but it's a number. We're trying to predict a number, not a category. And so we're going to go over through linear regression. So first, let's just look at some very basic data. So if we look at it, let it run. So while we let it run, I'll walk through what the code here is going on. Here we're just setting some X and Y variables, which are based off of our arrays. And we just have like 1 through 9, and then we just have some random values for it. And so what we're doing here is PLT is our matplotlib. And when we just call scatter, this is does a scatter plot. And so y'all are familiar with scatter plots, right? Just dots. So yeah, so we're just basically plotting in the X and the Y, and we're setting what the color of our dots are. And then plt.show just shows the plot itself. Do I need to refresh the page? Is it because I'm using? Yeah. Oh, let me. Scatter plot basically just like this. If you have your X and your Y, it's just like this. You just have scattering the points. That's all a scatter plot is, the dots. I think I might need to switch to Chrome. All right, y'all, give me 1 second. I forgot that the university's browser installs are awful. Please don't go emailing me. I get enough emails as it is anymore. I don't need more. I don't care. And so I'm gonna close that. I don't care. Bye. Got it. Yeah, thanks. Just get things up and running again. Yeah, sorry about that, y'all. I forgot that the university, I like to use Firefox as my default browser. Basically, not for the reason y'all might think, it's basically because 10 years ago I switched due to UI, due to the fact that I was 13 and I got angry at the UI that Google Chrome changed to. And I was like, fine, I'll never use you again. And so I switched to Firefox. So, okay. So now we should be able to plot. Great, cool. So as I said before, this basically we're making some arrays. We're just saying create a scatter plot and then show it. And so as you can see here, this is just arrangement of data. Would you say that this is linear? Like it's as it goes up, the other one goes up at the same rate. You could draw a line for that, right? Cool. So it's like broadly linear. So we need to, but like what line describes this? We want the best line possible to describe this, right? That would be the whole point of machine learning. We have our input and our output, and now we're going to make rules for it, right? So for that, we're going to first go look at our least squares. So our least squares estimate is basically just a very simple calculation, not the most simple, but code-wise it's pretty simple, of basically just the sum of the differences in the x values of the x inputs and the y inputs versus their mean divided by just the square of the x input. And so that will give us our slope. And then our intercept is just the output expectation minus the slope of the input. So we're going to write that code simply here. So first, we need to know, as you can see, we need to know how many data points we have. And so to do that, we're simply just going to do np.size x, because we're just going to encode our data as x and then our output as y. And so this is basically just gets the size of our data. If we had like a 2D array, which is like rows and columns, it would output a tuple, just two values. But since we have just one, just have a single list, it's just going to give us the size itself. So next, we want to calculate the means, the averages. So for that, NumPy lets us do that very easily, and we can just do np.mean x, and then np.mean y. So very simply, that just gets us our means for the values itself, very direct. And so next, we need to find the calculation of these top values and bottom values. These are also known as the cross deviations. So for that, we're just going to do SXY. And so for that, what we do the np.sum, but we're going to sum these values. And what we do is simply just the x minus the mx, which, if you remember, is our mean. And then we're going to do y minus my, right? Like we see above. And then we're also going to do SXX, which is just np.sum x minus mx. Whoops. Times x minus mx. And so this lets us calculate the tops and bottom values here, right? And so next, we want to calculate our slope. Then we simply just do the ss.xy by the ss.xx. And so now we have our slope. And then to get our intercept, we can simply do just the mean of our y minus the slope time our mean of our x. And so let's get our slope. And so to do that in Python, you just do print, and then we're going to do an f, which is just known as a format string. And we're just going to do slope, colon, and we're going to do curly brackets, slope, slope, and then intercept, colon, intercept. And what the colon curly brackets do is they basically just let us insert the variables themselves directly into the string. And so when we like print it out or do anything with it, it'll just call back to the value of the variables. So let's code it out. Let's print it out. Cool. Now we have our coefficient. We have a slope of about 1.17 and an intercept of 1.4. So you'll want to see what that line looks like, right? So to do that, we can first do our scatter plot again. This is just a fancier one where we're saying the color black. We're just saying the marker is a dot, and then we're saying the size of it. And then so if we want to calculate what we think the values are, then what we're just going to do is just do mx, y equals mx plus b. So we're going to take our intercept and then do plus slope times our x. And so this gives us a prediction of what we think the values are based off of the linear regression model we learned, which is just simply slope and intercept. So, and then we basically we plot it, we put in our x values and our prediction, and plot is just going to give us a line. And then we just plot then we just give to matplotlib, we just say for this axis, label it x, and this one, label it y. And then we just tell it to show the plot. And this is what we get. As if you got to the point, you should be able to see just black dots, and then you see a blue line that goes straight up it. And y'all would say that pretty much matches the line itself, right? Cool. Yeah, so that is our line. However, we need some way to, yeah? Yeah, I got you. That better? Yeah. Does anyone else need me to zoom it in more or no?
Is there a situation with co-laboratory just doesn't connect? Like at the top right, you have a little check mark, mine just says connecting. Entire time.
Refresh the page. That's weird. It should connect
Yeah.
automatically. Check your Wi-Fi then.
Yeah, I think this happened also like last time I tried to use it, so it might just be like.
That is odd.
When I think you have to think about the guys actually.
Hmm?
I think you have to think about the line actually.
Yeah.
Same time, so it's-
Yeah.
You scroll up.
Okay. Okay. So now that we plotted it, we need some way to evaluate it, right? That's the whole point. We need to know how good our model is. So we're going to use two types of it. We're going to do two sorts of metric. We're going to do the mean squared error, which I talked about before, and then we're going to do another one called R squared, which is also known as the goodness of fit. The mean squared error is what I described it was before. It's basically just the difference between our prediction and our truth squared. And so that's relatively obvious. R squared, which is the also known as the goodness of fit, is a statistical measure that basically just measures how much of the output variable, our y, how much it varies, is explained by the input features that we give it, our x, and the model we learned it from. So basically it says, for all the randomness of our y, how much can we explain it in the x? And so what we want there is that we want our goodness of fit, our R squared, to be high. Because if it's very high, then we can very well say the sort of patterns in the y that we're seeing, we can explain it with with x. And so the higher it is, the better we can say we can understand our data. So for this, we don't have to write this ourselves. This is where sklearn comes in, and it's very nice. So for sklearn, we can just use something like the means. So for mean squared error, we simply just have to call mean squared error and y and our y predictions from before. Yeah. And so we just call that, and that's our error. And then if we also want to call our R squared onto giveness of fit. Make sure closure shrinks. Then we can just do R2 score Y spread. And so we can run this. Make sure to spell it correctly. And as you can see, we have a 95% goodness of fit. And that is very good. That is exactly what we want. So great, we now have a model and it did decently well. But this is this is just pretend data, right? I'll let you finish. Let me fix that.
I got a mean square error of 3.15. I kind of just copied what you wrote.
Check your code here.
My line came out decent.
That's odd. Yeah. Sorry, I wish I had helpers tonight. Dang it, where did you go? Where did we say it?
Yeah, we have the same slope and intercept.
Did Jen check your intercept? Look at it. Yeah.
Yeah, it's the same. I figured out.
Okay, yeah. Yeah, that's weird. I'm not sure what explain that. But great. This was just some pretend data, right? This was something we made. Let's try something with actual data. So what we're going to do, we're going to work with some real data. This is the diabetes data set from scikit-learn. Basically, this is just a data set of about 400 patients that have diabetes. And they measured them after 1 year of progression to see how much their diabetes had progressed as like a quantitative number. And so based on that, they also collected some clinical data about them, basically their age, their sex, their body mass index, and then these other features. And so what we want to try and do is learn, okay, is there a way we can maybe predict how much someone's diabetes has progressed based off of these features, right? So for that, we're going to first need to get our data. We're going to go through the full pipeline, and this is first our data ingest. So for that, we're just going to grab diabetes, and we're just going to do data sets dot load diabetes as frame equal true. And as frame, it's basically just going to load it into pandas to make it look nice for us, which I'll show in a minute. So we don't let this run. And then next, we're going to do our standardization and splitting. So I talked before that we had 3 splits. You can also do 2 splits for simplicity. In case you're not really trying to do any sort of fancy testing, you just need to know, okay, learn something, then test on new. And so for that, we're going to do diabetes X train. So what we're going to do, we're going to define what our testing set in our training set is for both our X and Y. And what we're going to use is another sklearn function called train test split, which will automatically do the splitting for us. We're going to grab our diabetes.data, which gets our inputs, then diabetes.target, which is what we want to learn. And then we're going to say how much we want to learn. Let's say we want 30% of the data we have to be our test set. And then finally, I'm just going to set a random state so that we get consistent results. And so, cool. Then we did the split. Now, a very useful thing to do whenever you are doing machine learning is to look at how your training data looks like. For example, here we go here, sort of like what the training data looks like. It just values. And as you can see here, it's already been processed into what is called normalization, which is basically just fitting it to be within like a set range where the average is 0 and the standard deviation of 1 for those of you who took statistics. it's not. It's important to know if you're getting more advanced, but for now, just know we already have the data processed. And this is sort of what it looks like. Then we can also look at what our Y value looks like. And head, by the way, just lets us display our pandas like Excel spreadsheet. And just show us the first 5 rows. And so then this is what our output looks like. As you can see, it's just sort of like numerical values. There's no category, which lets us know this is a regression problem. So I'll scroll up here just to make sure you all see this. So next, so let's try and do linear regression. So yeah. Yeah. And don't worry, this file will also be released later in case you want to go through it by yourself. In case you missed something today and you want to go through it yourself, so don't worry. So let's try and do linear regression. So we saw before when we were messing with the toy data, basically we had one input and then one output, and we just learned a single line. Let's try that with that here. Let's just do very simple data. So here, what we're going to do is that, as you can see, we have a bunch of types of data. We have our age, our sex, our BMI, and then extra. So what we're going to do here is I have some code set up, and I'm just going to walk you through the most important part. If you want, I can explain after the workshop what some of this extra stuff is doing, but it's not vital for right now. So what we're going to first do, if we're going to, for our case, get our training data, which will be xtrain column. And this is basically this is basically just grabbing the specific column that we're looking at from our training data. Then this just grabs the values itself. And then this is a reshaping. And this is basically just putting it into a format that sklearn will find friendly. And then we'll also do the same for our testing data. So next, so now that we have our training and our testing data, we need to make a model. So instead of trying to write up our own fit curve and having our own slope and all that, we're not going to use sklearn again. So we're not going to call sklearn's linear regression. Simple as that. And then to train our model, just simply call linear regression dot fit xtrain, and then diabetes y train. And so this will automatically train our model for us. And then to get our predictions off of our test set, we just use our fit model and do dot predict, then xtest. So we're going to get predictions off of our x data, off of our y. And then to give some measure of our error, we're going to just call the same errors as we did before of our mean squared error against our test and our prediction. I see a message. So then we're going to do our mean squared error. And then we're also going to do our R2 score. Derwin, make sure to check above here that you didn't make any typos. So then we're going to do our R2 score of the same, diabetes Y test, and then Y bread. And so this is basically what this does is that this is creating a training set of just our input, of just our single column, and then same for our testing. Then we're making a linear regression model using sklearn, training it, i.e. getting that, that slope intercept, testing it off of data it's never seen before, and then we're measuring its output. And we're just doing that on each of the individual features. So once we have that, we can just run it. And so this will create a lot of plots for us. And I'll walk them through. Basically, this is just a basic plot of each individual feature against our metric to see if a single feature alone is very good at predicting what the diabetes is going to look like. So as you can see here, our error is high and our R squared is pretty low. Like it's 0.4, it basically has no way of predicting it. And so this is a great way of like analyzing how good our features are when you're feeding models in. BMI is pretty good comparatively. There seems to be definitely a trend. And then, so as you can see here, these individual features, not very good. They're not, they sort of can see trend, but they're not very predictive. And so the best feature, if we were to look at trying on just one, is BMI, but it just has just a 23% goodness of fit. We want to make that a lot better. So what we can do, that we can use more features. Who just says we have to use one? So with sklearn, that's very easy. All we have to do is just make another model, a full linear regression, just make another model. And then all we have to do is train it on all of our data. So what this is doing here is that if you remember before from up here, I'm just training basically on all of the features now and not just one at a time. So now that I have that, we're going to make our predictions again. So we make our predictions. And then we're just going to print out our errors. And then we'll also do our R squared. And then if we test it now, chaining off our feature, we can see that compared to just doing it on one BMI, on just BMI alone, we have decreased our error and our goodness of fit has increased by about 20%. It's very good. So what this shows us is that having more features in our data can actually be very good for our model because it helps us to have a greater understanding of our output. However, I want you to answer it. Do you think it's always true that having more features or more data, having more features to your data is better? Yes or no? How many of you think having more data is always better? I mean, having more features is always better. You do? You think more features is always better?
Saying data,
Oh, more data. Yes, these are all about more features. Do you think more features is always better?
not necessarily because they could figure out the feature.
You're smarter. You're smarter.
Thank you, Ben.
Yeah. So after this, so we've now covered regression, right? We now have a model that can predict a smooth line, but there's the other side of things. There's classification. And then classification is as obvious as it gets. Basically, given some features, we want to throw the output into a category. It's like spam detection, image classification, classifying apples and not apples and bananas, diagnosing whether someone has cancer or not, or trying to like group customers based on their behavior, or maybe the stock market. Say just bluntly if a stock going to be bullish or bearish. So for that, we're going to look at a different data set. For that, we're going to look at the IRIS data set. And the IRIS data set is a very classic data set of basically back in the 1930s, a professor basically studied 150 iris flowers of like three species of Setosa, versicolor, and virginissa. Can't speak. And he basically measured just features about their flowers of their sepal length and width and their petal length and width. And so what we're going to try and do is that based off of these four features, can we correctly predict what type of flower it is, right? So for that, we're just going to do what we did before, and we're just going to grab our data set again, and we're just going to do datasets.load iris as frame equals true. And so then we're also just going to do the splits again. We're just going to call a train test split again. And then we're just going to give it our data and our target. And then here, since there's so little data and I want to prove a point. We're gonna do a 50-50 split instead. Normally, you do something like a 70-30 or an 80-20 to give most of your data to the training set so it can learn it as best as possible. Over here, for demonstration purpose, we're gonna do a 50-50 split. And then we're also just gonna do random state again to make things consistent for everyone. And so we'll just split our data very quick. And then if we want to look, and if we would want to take a little peek at what iris looks like. As we can see, it basically just are 4 features of our sepal length, width, petal length and width. And then for our iris.target head, we basically got a few classes. As you can see here, this is just showing it as all 0, but if you want to describe that, basically we just have 100 features of different types, and it's just gonna be labels as 0, 1, 2. So maybe it'll be better if I do it as a bigger number. Let's just do 20. When putting a number here in head, it's going to you. How about we just show iris for my train then? There we go. There we go. That's better. As you can see in iris Y train, as you can see, there's like class targets of 0 to 1. They're just classifications of what type of flower it is. So cool. We have some data, we have our inputs and outputs, but we need to have some understanding. And since we're doing classification, we kind of want to see how these data gets aligned together. So what we can do is that we can use Seaborn to do what is called a pair plot, which is going to compare one variable against another directly. And so for that, I'm going to do a little bit of coding first. What I'm doing here is I'm basically making a copy of my training input. And then I am adding our target feature back in. And I'm doing this purely for visualization purposes. This is not used afterwards. And so what we can do is we can call SNS.pairplot. And then we just do our visual train. And then our hue is target. And this will, and then as you can see, once we run this is going to basically just shade the dots in a way that makes it obvious like which target we're looking at. If you don't mind me, if I move out, like, zoom out here. Now we have a bunch of different plots where we're basically comparing our input features against one another, and we're coloring them based off of our outputs of whether the target classification is 0, 1, 2. So based on this, do you think that there's some pairs of data where the separation is very easy, such as here, versus where it's very hard, like here? Like you can't easily split it here, but you could pretty easily split it here or here. And then you have ones like you have one like this that's kind of hard. So, or like ones like this, you can't really split on this at all, can you? So this, what pair plots do is they let us observe our data directly, and they kind of give us an understanding of if we were choosing which features, which ones do we want to use that would give us sort of the best information. So what we're going to do now is that we have our plots and we have like an idea of which ones we expect to do well. We're going to go down here. And so like we before, for our classification, we're using logistic regression. It's basically the same as linear, except we're now just putting it on a curve. So for this, we're going to have our code here. And so I can also explain this after the workshop if you want me to. All you need to know is that we're going to first grab our training set. So what we're going to do here is we're basically just going to test pairs of value. Since we see that these groupings are super good, some of them are good, some of them are bad, well, just test them. Like, do we know if petal width and petal sepal length are going to do very good? Like, it may look good on training, but won't look good on testing. So we're going to do our iris-X train, and then we're just going to index it. And we're going through the same column, like the sepal width and sepal length up here. That's what our looping is for. And we're basically just saying, grab these 2 columns. Just grab these 2 features. And so what we're going to do is now we're going to make our logistic regression model, which with sklearn, it's very easy. You just write logistic regression. And so like before, we do log model dot fit. And then we do our X train, and then we do our iris Y train. And then we'll just do the same before. We'll just generate our predictions off of our iris Y test. And then for our metric, instead of doing the mean squared error or R squared, we're not going to do accuracy, which accuracy is pretty obvious of the number of correct answers you have divided by the total number of answers. Like basically whenever you do a test, like if you got something out of 100, it's the number of correct answers you have out of the total number of questions. So for that, that's also very easy. We just call accuracy score, then iris Y test, and then Y pred. And so now that we have our model code set up, let's run it. Why are you yelling at me? No. Why are you yelling at me? Oh, whoops, don't fix this. It's X test. That's my mistake. I was not paying attention. So let's try that again. So now we're basically just we're teaching our logistic regression model on all these potential pairs. And now I'm plotting them out on which one's best. So what you're looking at here is basically every potential pair on our test data and basically lines on how our logistic regression model has learned to split it along with an accuracy score. For example, here, this is our 3 classes. And as you can see, these sort of yellow and blues, they're very mixed up. And so it's a kind of low accuracy because it's classifying things wrong. Because the model thinks everything here should be blue, everything here should be red, and then everything here should be yellow. But that's clearly not true, right? Like the dots themselves are the ground truth, and so there's some incorrect. But other features are doing very well. Like when on petal width and petal length, that's a 96% accuracy. That's very good, right? So here, depending on the features you choose, your model can do very poorly, or it can do very well, right? So what do you think we should do next? Do you think we should test on all the features? Yes. But let's try it. Because as we saw with our linear regression, more features led to a better result. So by that logic, it should be the same here. So we're going to do our full log model, logistic regression, and then we're going to fit it on everything. So like before, instead of indexing anything to get a set of features, we're just going to train it on everything. And then we're going to just, and we're going to do predict on our testing data. Then we're going to get our accuracy score. And then we're going to just print our accuracy when trained on all features. And for here, I'm just going to take our accuracy, multiply it by 100, and then just do a little cleanup code so that it will print out nicely. All this does, it basically says, hey, print out to only 2 decimal points. It's just convenience. So let's train our model. Why are you yelling at me? You're wrong. Oh, whoops. There we go. That's better. So when we trained our model on all of our features, we get a 93.33% accuracy. That's worse. We have a 96% right here on just 2 features. And now adding more data, adding more features, we've done worse. That doesn't make any sense, right? So this highlights a very important thing, that just because you have more features for a data point, like you add more information, doesn't mean that you've done better. Like, as we already saw before, like the sepal width and sepal length, this combination together, it's just noise. And when we saw in our plots, the sepal width is just sort of everything overlaps. So it's clear like this feature is not great. So by adding this feature into our models, we're trying to teach our model what I talked before, noise. We're trying to have it also learn how to split things based on this, And because the model can't split on this, it affects how the model learns everything else. Because not only is the model trying to learn just all the other things, it has to learn this. And so it's trying to do the best of the average of all of them, and so it performs worse. So what this shows that you can't just give everything. You have to know what you're inputting. You can't just go in blindly and say, it's more data, so everything's perfect. No, you have to look at what you're doing. You have to always look at your data and know what you're putting in. So another thing that can be very useful is like knowing what it got wrong, right? Like you can't just know, like, sure, we have a number, but we don't know what's going wrong. Like, for example, if we were classifying apples and bananas and our test set had 8 apples and 10 bananas, 8 apples and 2 bananas, and we fed it through and the model got an 80% accuracy, do we know what that 80% is? Like, did it miss the 2 bananas? Did it miss 1 banana and 1 apple? Or did it just miss 2 apples and got the bananas right? We don't know. We just see the number. So what we can use is something called a confusion matrix. And what a confusion matrix is, it just checks against what the actual value is of our output versus what we think it is. So I'm just going to call confusion matrix Y test, and then Y prediction. And then we're just going to do display, and confusion matrix display. And all this is that this is another tool that sklearn provides to display the confusion matrix it generates. And then I'm just going to feed in the same flower types that we did before, so we can understand which flowers it's confusing. And then we'll just do display.plot. And then plt.show, but we always got to show them. And so once we run it, we now get a confusion matrix. And as you can see, we have our true labels and our predicted. And as we can see, for our 21 setosas, it predicts them all correctly. For our versicolors, it thinks one of them is Virgicina. And then for our Virgicina, thinks 4 of them are versicolor. So as can be seen, the main issue of our model is that it can sometimes confuse versicolor and Virgicina. And so confusion matrices are very useful in helping us really understand where our model is making mistakes. And so whenever you're doing analysis on classification, it's always useful to do a confusion matrix so you can actually see which ones it's making a mistake on and not just get lost in single numbers. And so as to just press again as a final warning, correlation is not causation. Just because you have an input that looks similar to an output doesn't mean that the input causes the output. So you should always be very careful on the conclusions you make on your machine learning models and as the data you feed in. Once you have a model and that you see it performs well, it's always good to do a deeper look at why the model fit well. And as always, understand your data. The more you understand your data, the better you can use your model. Thank you everyone for coming tonight. I am grateful appreciative of the crowd. So if you can, please fill out this questionnaire that I linked at the bottom so we can get some feedback on how we did tonight. And please come back in the next 2 weeks where I'll be going over Machine Learning 102, support vector machines, pay nearest neighbors, and decision trees. Basically, the advanced next step of the model we learned here. Thank you, everyone. Yeah.
Maybe same time and room.
Same time and room. No, it's MSP 306 at 7. Let me say, right now it's MSP 306 at 7 o'clock. Things may change, but not for the next meeting. The next meeting is at this time, at this same time. Thank you, everyone. Have a great night.